If power is the lifeblood of civilization, why stop at fossil fuels, fusion, or even planets when you could capture your star itself? What is a Dyson Swarm? When we talk about building a Dyson Swarm, it helps to start by clarifying exactly what we mean. Popular culture often depicts a Dyson sphere as a massive solid shell encasing a star, a vast megastructure of unimaginable scale. But in reality, that classic solid sphere was always more of a thought experiment and one of the significant engineering problems. It's unstable, impossible with any known material, and worse, there's no gravity inside it except the sun's, meaning everything, air, water, and people, would fall straight into the star, not exactly ideal for long-term habitation. That's not to say the general idea is impossible. There are alternative approaches, like arrays of tilted and rotating ring worlds, that might achieve a similar effect without the same fatal flaws. But what Freeman Dyson actually proposed was far more practical and arguably far more ambitious. He envisioned a swarm of individual structures, countless solar collectors or habitats orbiting independently around a star. Each piece gathers a fraction of the stellar output, but collectively they could capture most, if not all, of the energy a star produces. This distinction matters. A Dyson Swarm isn't a rigid sphere, nor is it a continuous shell. It's a cloud of technology orbiting like a vast artificial solar system. Millions, billions, even trillions of satellites, habitats, or power collectors sweeping around the sun at various distances and inclinations. It is modular, expandable, repairable, and most importantly, it is buildable, at least in theory. In other words, it is not science fiction, it's just a project no one's tried yet, at least no human. And hunting for Dyson swarms, also called Kardashev 2 civilizations, is one of our major approaches to SETI, the search for extraterrestrial intelligence. Today, we'll look at how we might actually build a basic Dyson swarm, and how it could grow and transform over time. Early swarms might gather only a fraction of the sun's light, made mostly of thin solar collectors rather than habitats, but over time, those elements would evolve, expanding, diversifying, and capturing more sunlight. It is also not a dense or cluttered space. It is not a metal shell. It's a forest of steel and sunlight. Think of it less like wrapping a star in a steel cocoon and more like surrounding it with a cosmic forest of space stations, each soaking up sunlight like leaves on a tree. Down beneath the canopy, the light making it through all those scattered layers of leaves dims appreciably. Same concept, only instead of growing food, these leaves are growing power, feeding industry, computation, or entire civilizations, and ones of such scope they dwarf any empire we have ever had. Of course, some might still grow food, serve as homes for humanity, or act as nature preservers, or fill any of 100 other roles, common or rare. A Dyson Swarm is more like a city than a building, though far less dense than even the most rural countryside here on Earth. Instead of forming a thin shell around the sun, it fills a vast volume stretching hundreds of millions of miles deep. Even the densest Dyson Swarm would be more spread out than the population of Earth's remotest regions, and yet it would also use up all that sunlight, and sometimes even recycle it. We see this in a specialized variant known as the Matryoshka brain, a stellar engine devoted entirely to computation, where the waste heat of each layer powers the next. Layer upon layer, energy is reused, 12 times or more. In a Matryoshka brain, waste heat isn't waste at all, it's just tomorrow's power source. See our Jupiter Brains and Megaminds episode for discussion of these and other astronomical scale computing options. Whatever form a Dyson Swarm or stellar engine takes, the concept remains the same. Capture every bit of power you can. After all, our sun gives off 2 billion times more energy than ever reaches Earth, a staggering amount, and Earth's relatively tiny supply is still many times more than we use to run our entire civilization. It's that breathtaking potential, tapping directly into a star's entire output, that elevates this concept from mere megastructure to a true measure of a civilization's power. As we mentioned, the concept ties directly to the Kardashev scale, a method proposed by Soviet astronomer Nikolai Kardashev for measuring a civilization's technological advancement based on energy usage. A Type 1 civilization harnesses the energy of its planet. A Type 2 civilization captures the full power of its star. And that's what a Dyson Swarm represents, the threshold of Type 2. We explore just how staggering even a Type 1 civilization's scale is in our episode The Kardashev Scale in Population, and the leap to Type 2 and 3 only grows more unimaginable. This is a pathway of immensity and mega engineering beyond anything we've ever attempted or even dreamed. It is not just an engineering challenge, it's the ultimate symbol of a civilization that has outgrown its planetary cradle. A Dyson Swarm turns a single star from a distant point of light into the lifeblood of a civilization that spans an entire solar system, and as we'll see, it might be the first major step toward conquering the stars themselves. Because once you've turned your sun into an engine, the stars stop looking like distant dreams and start looking like your next destination. Gathering the materials. Of course, before you can build a Dyson Swarm, you need the raw materials, and a lot of them. We're not talking about mining a few asteroids or hauling up steel from Earth. If all we want is thin solar collectors, that might be sufficient, but a true Dyson Swarm will require more matter than every building, vehicle, and mountain on our planet combined, many times over. Indeed, it may take many planets. We'll get to that in a moment, but for the simplest case, let's imagine we're trying to encompass the Sun in a reflective sphere. Normally, a Dyson Swarm is a cloud of individual objects rather than a solid shell, but in point of fact, a thin enough reflective surface can essentially float over the Sun. Much like a solar sail, sunlight itself can support it. We call the stationary version of such an object a statite, short for static satellite, which hovers in place by balancing solar gravity against solar pressure. This is the radiant pressure exerted by photons as they hit something, and if it's reflected, they bounce off and give it double the shove they would if only absorbed. There's also the lagite, a similar structure that orbits the star, but much slower than gravity alone would allow, lagging behind thanks to solar pressure. Neither approach is mandatory for a Dyson Swarm, but both showcase how sunlight itself becomes a structural tool, not just an energy source. You can check out our Statites and Lagites episode for more on that concept. Importantly, materials designed to collect or redirect sunlight do not need to be placed as far from the Sun as Earth. Plenty of common reflective metals remain effective even at just a tenth of that distance without melting, and since a sphere at a tenth of Earth's distance has 1/100th the surface area, the required material shrinks dramatically. In the vacuum of space, where there's no oxidation or weathering, materials like aluminum can be astonishingly thin. A reflective shell just 50 nanometers thick, thinner than a human hair by orders of magnitude, would suffice. With aluminum's density of 2,700 kilograms per cubic meter and an area of 2.8 times 10 to the 21 square meters at that distance, the total mass of such a shell comes to about 3.8 times 10 to the 17 kilograms. For context, Earth is 15 million times more massive than that. Even the Moon is nearly 200,000 times heavier, and Ceres, the largest asteroid in the belt, outweighs it by a factor of 2,500. So even if we built it with 10 times the material for redundancy, we'd barely scratch the resources of a large asteroid, let alone a planet or the solar system as a whole. And that's already a useful bit of stellar engineering. For instance, if we moved just the equatorial band, or better yet, did that and placed a structure around a dimmer star, the reflected light could boost the star's surface temperature, making it shine brighter and pushing its habitable zone outward, at the equator. We call this star boosting, and the material cost is surprisingly modest, roughly the mass of a medium metallic asteroid about 40 miles or 65 kilometers wide, something like the asteroid 433 Eros. A smaller star would also require less material. You could even leave a hole in one side of the sphere, letting light escape in a specific direction. This effectively turns the structure into a Shikata thruster, a stellar engine capable of nudging the entire star, and any worlds bound to it, across the galaxy over millions of years, or even to other galaxies. They are slow to accelerate, but can get to a decent fraction of light speed. At this point, all we've done is to redirect sunlight. Even at this basic level, the potential is enormous, but any further tasks, like converting that energy to electricity, would add more complexity and mass. Proto-Swarm, our first steps. Before the grand ambitions of mining Mercury or harvesting Jupiter, our first steps towards a Dyson Swarm would be far humbler and far more familiar. The earliest phase might resemble an expanded version of today's space-based solar power, orbiting satellites capturing sunlight and beaming it down to Earth, the Moon, or Mars. Built from lunar regolith or near-Earth asteroids, these stations would form the first bricks of a solar economy. Over time, we'd begin converting those asteroids into space habitats, powering them with beamed energy, and adding new habitats and megastructures in orbit around Earth and other planets and moons. We've discussed before the concept of a planetary swarm, a mini Dyson swarm built around Earth, contained within the million-mile sphere where objects orbit Earth rather than the Sun, called the Hill sphere, bounded by our Lagrange points and close enough for real-time communication. This volume alone receives enough sunlight to support the living area of 50,000 Earths, or 40 billion O'Neill cylinders, or many times that in other habitats like the Stanford Torus. And yet, even lavishly landscaped habitats built at that scale would barely scratch the resources of the Moon. Even in this early era, you're likely already sending colony fleets to new star systems, and with a planetary swarm, that process becomes trivial. At that scale, building thousands of self-sufficient Ark ships is simply routine. Any one of those habitats could serve as a colony ship, and when you're producing them by the billions, dispatching thousands to robustly settle nearby systems is child's play. And unlike fragile interstellar probes, these are full habitats, capable of surviving for untold centuries or millennia, taking entire ecosystems and societies with them. Massive arrays of solar collectors easily power the pushing beams needed to send those arcs racing toward the stars, and yet this is still small compared to a true Kardashev Type 2 status. A full planetary swarm might be vast beyond current imagination, but is still tens of thousands of times smaller than a full Dyson swarm, and just a prelude to capturing the full power of our Sun. Beyond the planetary swarm, we might one day build a Terran ring, a vast ring or donut of habitats circling the Sun at Earth's orbital distance and along its path, physically connected by tethers, even made of mundane materials, allowing fast and cheap flow of people, power, and information throughout the ring and back to Earth. Earth and its planetary swarm would shine like the gemstone of that ring. The beauty of both ideas is scalability. A Terran ring can start narrow, requiring minimal mass, but grow wider over time as resources and ambition allow, becoming a true bridge between Earth and the wider Dyson swarm to come. Eventually, we might expand it by adding more sun-wrapping rings, tilted at angles, much like the concept of stacked or inclined ring worlds, but without the need for hyper-strong materials. You can also use those to widen your ring off Earth's orbital path, as those varying from it would be perturbed, but would have that balanced out by being tethered to other habitats who were off orbit in the opposite direction. With every new station added, the system would grow, scaling up our industrial might until mining Mercury or building statites no longer feels like science fiction, but simply the next logical step. Mining the solar system. Fortunately, the solar system is vast, and it's absolutely packed with material just waiting to be used. If Earth is our cradle, then the asteroid belt, the Kuiper belt, and even the gas giants represent the quarries we'll mine to leave it behind. Mercury in particular often comes up as a prime candidate for dismantling. Rich in metals, close to the sun, and already baking all that solar energy, it's well positioned for heavy industry. As we move beyond simple collectors and start building complex Dyson Swarm elements, power beaming systems, transmission relays, and habitats, our appetite for raw materials will quickly outstrip what a single medium asteroid can offer. That's why, as ambitious as it sounds, many envision what we might call the Mercury strip mine approach, disassembling the planet piece by piece, refining it in orbit, and launching the component sunward to assemble the first-grade solar collectors. It might sound extreme, but compared to the solar system's vast reserves, Mercury is just a tiny fraction of the available mass. Sacrificing one small planet could fuel a civilization vastly larger and more numerous than anything 1,000 planets could support, or 1,000,000. It's not destruction, it's metamorphosis. Mercury becomes the seed stock for a civilization that spreads beyond the solar system, transforming a barren world into the backbone of a stellar empire. Beyond Mercury, the true scale of the swarm. And Mercury wouldn't be the only target. As we begin creating ecologies and landscapes inside vast rotating habitats, we'll need the full range of building blocks for life, materials Mercury simply can't supply in abundance. The asteroid belt offers rich quantities of metals and silicates, ideal for space habitats, stations, and industry closer to Earth. When it comes to water, ammonia, and carbon compounds, essential for life support, biospheres, and fuel, we'll turn to the moons of Jupiter and Saturn, rich in ices and organics. Beyond them, the Oort cloud may hold entire planetary masses of water ice waiting to be harvested, along with other volatiles. Even the mighty gas giants themselves could be future targets. Jupiter holds more mass than everything else in the solar system combined, except for the Sun itself, which contains 99.8% of all the mass in our system, including thousands of Earth's worth of heavier elements like metals. Those too can be harvested through starlifting, using a combination of solar-powered magnetic fields and massive mirrors to extract material directly from the Sun's outer layers. That's a leap beyond mighty asteroids or moons, true stellar engineering, but entirely feasible given enough time and energy, no new science required. We deep dive both in our episodes Harvesting Planets and Starlifting. It is a slow process. Harvesting a gas giant or a star might take hundreds of thousands or even millions of years, but time is a luxury for a civilization on this scale. After all, even the universe itself has only just begun its story, and a civilization wielding entire suns has the leisure to think in millions of years, when building a civilization around a star meant to endure for billions more. And every star system should have enough mass in its own star to build a Dyson Swarm, plus some rocky bodies to jumpstart the starlifting infrastructure. If not, a basic Dyson Swarm already allows you to ship material across interstellar distances, riding the captured sunlight itself, and it would be well worth importing enough material to set this up if some metal-poor star lacked even any native asteroids to work with. Ironically, Earth in our solar system might be one of the few places where importing rocky material in massive quantities from other star systems becomes worthwhile. As we speculated in the past, this could be a common arrangement for early interstellar settlers. Earth funds the colony ships and grants rights to new star systems, but in exchange, those colonies agree to send back several times as much material as was used to build their fleets. Likely they would keep trading back more raw materials in exchange for information, science, and entertainment from the homeworld and its suburbs, and they may strike the same deal with their own future colonies even further away from our homeworld. And over time, that trade, raw materials flowing back from the stars, might be what lets Earth grow into a full Dyson Swarm primarily made of space habitats. And once that interstellar flow begins, it becomes the spine of a galactic economy, each star system a node feeding the collective growth, not just of Earth, but of humanity's entire stellar network. But that's a very late phase operation. For a starting point, we don't need to harvest the entire solar system, just enough to get our first foothold. A Dyson Swarm, after all, does not need to be completed in a single push. It's modular by design. We can build it one satellite at a time, one station at a time, with each new collector adding to the system's power and resources, helping bootstrap the next wave of expansion. That's what makes the Dyson Swarm so elegant. It's not a single mega project, it's 1,000 smaller ones, growing and multiplying like a living ecosystem. At first, it might be no bigger than our largest satellites today, just thin solar sails or panels, harvesting energy and beaming it back home, barely scratching the total solar output. But as our industrial capacity grows, so too does the swarm, expanding outward, layer by layer, until it surrounds the sun. And the beauty of this approach is that at no point does it require some magical material or impossible leap in physics. The resources are there. Even ideas like starlifting or interstellar shipping rely on physics we already understand, scalable with time and energy, not miracles. The basic science is known. All that stands between us and the stars is the will to begin. We've seen today that building and operating Dyson Swarms is a lot more plausible than people tend to assume from the sheer scale, and life can seem like that sometimes too. Overwhelming, but a lot easier when you start breaking into manageable bits. It also helps if you have some humor in your life, and if you're looking for some humor that is simultaneously relatable and surreal, check out Amy's Dead-End Dreamhouse. Starting with episode 1, Total Career Collapse, we follow our protagonist trying to juggle 2 jobs and getting fired from both, then trying to start a new life with the advice of household appliances. It's witty humor and sketch comedy, along with a healthy dose of millennial angst to tackle everything from job hunting to depression. And they've just released a new episode, Ghosts of Friendship Past, where Amy is sent a mysterious letter in the mail from an ex-best friend and concocts an elaborate plan for revenge. Amy's Dead-End Dreamhouse is just one of the dozens of top-tier Nebula originals you'll find when you join Nebula. You also get every regular episode of SFIA early and ad-free, plus over 50 Nebula-exclusive SFIA episodes, full-length deep dives that have been releasing monthly for years, along with extended editions, bonus content, and amazing work from many other creators. Join today for just $36 a year or $3 a month. That's 40% off. Head to go.nebula.tv/IsaacArthur and start watching now. Building habitats. How much mass do we really need? Now, this idealized Dyson Swarm of habitats takes vastly more mass than simple solar collectors. You might even choose to star-lift material from the sun itself, reducing its mass to extend its lifespan, while using polar mirrors and equatorial living bands to make the most efficient use of that material. There's less living area, but far less mass required on a longer-lasting sun to power it, especially with star boosting keeping the star bright and shiny in the spectrum we prefer. Needless to say, some more advanced cloak tech that lets us transmute hydrogen and helium in bulk into building materials would make this process easier, but it is not necessary. For large-scale habitats, mass estimates can vary widely, from a few thousand kilograms per square meter to hundreds of thousands, depending on design, structure, and shielding needs. If we simplify the math and calculate the required land and sea area based on a true Dyson sphere, one large enough to receive the same solar flux Earth gets, we hit staggering numbers. The key is remembering that Earth only intercepts a fraction of the Sun's light, determined by its cross-sectional area, pi r squared, while its total surface area is 4 times greater, 4 pi r squared. So, to recreate Earth-like living conditions around the Sun, we need a Dyson sphere with 4 times the area Earth's orbit intercepts, or twice Earth's orbital radius, to achieve similar temperatures, which is well out past Mars, incidentally. That works out to be about 1.13 times 10 to the 24 square meters, which is roughly 435 quadrillion square miles, or 278 quintillion acres. That's 278 billion acres of potential living space, a whole planet for every person currently alive. For mass, even at the low end, assuming just a few thousand kilograms per square meter, we're looking at around 3.4 times 10 to the 27 kilograms. That's 568 times the mass of Earth, or nearly twice the mass of Jupiter. And remember, Jupiter is mostly hydrogen and helium, useful as radiation shielding or combined with oxygen to make water, but less so for solid land. Oxygen, the third most abundant element after hydrogen and helium, though a distant third, is critical here, forming both water and rock. It's also 89% of water's mass, making water relatively easy to produce once you have hydrogen. In practice, much of that hydrogen would end up in honeycombed outer layers of habitats, serving as excellent radiation shielding, because we have far less oxygen and want to use around half of it for making rock. Given that Earth's surface is mostly water, it's likely our Dyson Swarm would include vast aquatic habitats, simply because hydrogen needed for water is easier to source than metals and silicates needed for dry land. Now, some argue that there just isn't enough mass in the solar system to build a fully inhabited Dyson Swarm, and certainly not one with thick Earth-like landscapes, but that often ignores 2 key points. First, that the galaxy has plenty of raw materials that we can import to this most precious star system. If you mine and refine that material into dense, shiny payloads, you can build solar-powered beaming stations at both ends, one to push and one to slow it down upon arrival. That setup could theoretically accelerate 1 billion tons per second to 1% of light speed using our own sun or a twin. Of course, since we have to decelerate here on arrival, regardless of how many systems contribute, that's more or less our maximum sustainable import rate. Even so, at that pace, it would take about 200,000 years to import an entire Earth's worth of mass. Impressive given the scale. Ironically, that timeline could be shortened by shipping the material slower, at 0.1% of light speed. It would require just 1/100th the energy, allowing us to break an Earth's worth of materials in as little as 2,000 years. Alternatively, we could send aboard vessels carrying their own reaction mass for deceleration, or even beam in energy from other systems to help slow it down upon arrival. Second, we shouldn't forget that our own sun contains nearly 6,700 Earth's mass worth of heavier elements, not hydrogen or helium, much of it oxygen. That's more than enough for rock, soil, and water. Even if we built our ground layers 10 times thicker than the minimum, consume your 500 Earth masses, we'd still have thousands of Earth's worth of material left over. Timeline-wise, even if you devoted every drop of the Sun's energy to disassembling it and filtering out its mass, it would take about 19 million years of solar output, and that timeline would only stretch longer as the Sun's power dropped during the process. Plus, you probably are using a lot of that power for other things. From this, we can conclude that, at least for this first and most important star system, the bulk of mass is likely to be shipped in at less than 1% of light speed from other systems, and likely take no less than 10 to 100,000 years to reach the point that most light is going onto habitats, assuming humanity is still interested in such things by then. We would still be nowhere near colonizing the galaxy at this point either, though we may have gotten probes out to nearly all of it and settled a few thousand light years all around, maybe even a billion star systems. This is also a great way to deal with bigger and shorter-lived stars. You use their own energy to mine them down to a longer-lived and more useful star, and then ship out the excess mass to where you want it. Bigger stars are problematic too, as part of the reason for their short life is they are not very convective. While they still have plenty of heavier elements in their upper layers, the fusion byproducts they make while burning stay in the core till they go supernova. The Sun is convective, at least somewhat, so heavier materials aren't just buried in the core, they are bubbling around like a pot of stew. Still, you'd have to be patient to extract them all. I could even imagine a Kardashev Type 2 civilization building pairs of suns, draining matter back and forth between them, siphoning out the heavier elements and even helium to keep them clean and optimized. Sounds insane, but so is the scale of such civilizations, the power they wield, and the timelines they operate on. Now, that's all further down the road, but it's not actually beyond our understanding. Starlifting and laser sails are both grounded in proven physics and existing technology. Of course, actually doing them would come with plenty of unexpected challenges. Engineering always does. But even if we somehow fell short of the mass needed for a full Dyson Swarm, why would that stop us from building as much as we could? A Dyson Swarm doesn't need to capture or use 100% of the Sun's light to be worthwhile. Capturing just 1% for habitats and 99% for solar collectors would still give you a civilization tens of millions of times larger than Earth. Ultimately, you build what you can. You expand as your capabilities grow, extracting more from challenging sources like Jupiter's depths, the Sun's outer layers, or even from other star systems. A Dyson Swarm is not a finish line, it's the starting point of building civilization on a cosmic scale. The long dawn of a stellar civilization. In the end, a Dyson Swarm isn't just an energy project, it's the first step toward becoming a civilization that no longer fears the dark. Fitting, because as we build swarm after swarm around new stars, the galaxy itself will grow dim, its light consumed by our ambition, as we creep toward becoming a Kardashev Type 3 civilization. That doesn't mean some unified galactic empire. Lightspeed ensures each system remains its own world, but every new colony, every new star, will have the same motivation to repeat the process, a civilization measured not in nations or planets, but in stars. It all begins humbly, just a few satellites sipping sunlight, but if we endure, if we reach, that seed becomes something vast, with each new habitat, factory, or collector added to the swarm. We grow less dependent on Earth and more at home in the cosmos. Each ray of light captured, each atom rearranged, carries us forward, until one day our cradle is just a glimmer lost in a sea of shining worlds built by our hands. And beyond that, the stars themselves open up before us. Not distant dreams, but destinations. When your civilization feeds on a star, crossing to the next is no longer a fantasy, but the obvious next step. One star becomes many, one swarm becomes a network, spanning the galaxy, each node a home, each light reclaimed from the void. That is the promise of a Dyson Swarm, not an end, but the ignition of something far greater. A civilization that no longer counts its future in generations or centuries, but in stars claimed, worlds built, and light gathered from the deepening dark. Until one day, we are no longer the children of Earth, but the children of the stars themselves. After all, why should the stars remain the silent audience to our story when they can be the stage upon which we build it?